Greetings. Let us continue with the analysis of a redundant frame. Numerical number 10. Analyze the truss shown in figure. Take AE as a constant. The given frame is a single bay frame having support over vertical wall. Joint A is having hinge support, whereas joint D is being with a roller support. At joint B, the vertically downward load W kilonewton acts. The bay width is about 4 meter, height of the frame is 4 meter. It is supposed to find out member forces within this assembly. To begin with this, we will first verify whether the given truss is statically admissible or not. So we will call that step as a verification of determinacy, where we will find out the degree of static indeterminacy of this truss. For that we will make a count of number of members. Number of members are 6: A, B, B, C, C, D, D, A, A, C, and B, D. Number of reactive forces due to end resistance are 3, 2 at the hinge support and 1 as the roller support, H, A, R, A, H, D. Number of joints are 4 here, A, B, C, D. If we put in the relation here, ds is equals to dse plus dsi. DSE stand for external indeterminacy, whereas DSI stand for internal indeterminacy of the truss. External indeterminacy is equals to number of unknown forces minus available equilibrium equation. Unknown forces are 3. Equilibrium equation is also 3. 3 minus 3 comes to 0, means statically externally it is determinate, but well, we'll see the internal indeterminacy. We have a relation m minus 2j minus 3. 6 minus in bracket 2 into 4 minus 3 result into a value of 1, means one member force is in excess. That says that degree of static indeterminacy of this truss is equals to dse plus dsi, which comes to be 0 plus 1 equals to 1. Now if we want to analyze this, first we have to make the structure as a statically admissible. To do so, we are supposed to remove one of the member. Let us say member BD has been removed to make it a statically indeterminate. While doing so, the effect of other members should be unaltered. For that, we are going to apply equal and opposite force at the joint B and D in the same line of action, so that the effect of this member force will get unaltered. After removal, it will get unaltered. Once we got the statically your admissible case, then we are going to find out the end reactions. For that, we will apply static equilibrium equation to the whole geometry. From equilibrium of horizontal forces, we get a relation HA plus HD equals to 0. HA is going towards the right hand side, HD is going towards the right hand side, equals to 0. There is no external force applied at the in horizontal direction, that's why it comes to 0, which says that HA is equals to HD but opposite in nature, equal in magnitude. That's why we can say the direction of HA should be changed. Now if we take equilibrium of vertical forces, we have relation Ra minus W equals to 0. Ra the reactive force generated at the end A, and whereas W is the vertically downward load, here we can say Ra equals to W kilonewton. Now I will use the third equation, summation of moment at the joint D equals to 0. We will take the effect of the forces around the joint D, HA into 4 perpendicular distance with reference to joint D. It will give a anti-clockwise twist, that's why minus 4 into HA plus W into 4, this will give the clockwise twist, plus W into 4 equals to 0, resulting in the value of HA equals to W kilonewton, HB equals to W kilonewton. Thus we have got all unknown reactive forces here. Once we have got unknown reactive forces here, we will move with the P force analysis. We are going to say it is the forces which is being carried by the member in a statically admissible case. So for that, let us say P1, P2, P3, P4, P5 are the forces in respective members. Now I will find out the inclination of inclined member with reference to horizon, that is angle intercept within the inclined bracing here. If we take geometric consideration here, it will be tan inverse of AD, tan inverse of AD by CD. So it is 4 by 4 comes to 45 degree. Now I will apply joint by joint analysis here. To begin with, we will start with the joint B. If we prepare free body diagram at joint B, we have three forces: W kilonewton going downward, P2 force in the member BC, and P1 force in the member AB. Now if we write summation here static equilibrium equation for this free body diagram, we get summation of Fx equals to 0, P1 minus 0 equals to 0. Since there is no horizontal force, that's why P1 value comes to be 0 kilonewton, means member AB will have 0 force. Whereas if you go to the vertical direction, we have the member force P2 going upward minus W, the vertically applied load, that's why P2 result to be W kilonewton in compressive nature. That's the member force in BC is W kilonewton. Now after completing the joint B, we'll move towards the next joint C. At joint C, we have three members generating member forces like P2, P3 and P4. Among this P2 we have just evaluated from the analysis of joint B. So what I will do, I will write a static equilibrium equation for the joint C here. Summation of force in vertical direction equals to 0 result into P3 sine of theta going upward minus P2. Here by typographical mistake, let's consider this cos theta as a sine theta, resulting into value of P3 is equals to P2 divided by sine theta, which comes to 1.414 W kilonewton tensile in nature. Whereas if I apply a static equilibrium equation for the forces in horizontal direction, we get P4 minus P3 cos of theta, means component of P3 along horizontal direction moving towards the left hand side, that's a negative, resulting into value of P4 as a W kilonewton compressive in nature. Now once we know these forces, we'll mark the forces on the member for a ready on the figure for a ready reference, and we'll move towards the another joint. Then in joint D we have two forces P4 and P5. Among this P4 we have just evaluated, unknown is P5, that's why I will write static equilibrium equation for only vertical direction. The summation of vertical direction equals to 0, P5 minus 0 equals to 0, since there is no vertical force to balance this P5 member force, a member AD member force, that's why member force AD will be 0 here, P5 comes to be 0. So likewise we have completed the estimation of forces in all members with reference to statically admissible case. Now when we apply the unit load effect here, so what we will do here, we will apply a unit load at along the member BD in such a way that it will have the same effect as the original member BD is supposed to have. So let us consider I have applied unit load here instead of redundant force X. I have applied unit load at joint D and B in tensile nature, and I will try to find out the contribution of this unit load among all the members. For that, we'll have the joint by joint analysis with reference to effect of this unit load. If I will move with the joint B, if I write static equilibrium equation for joint B, it will be summation of Fx equals to 0, K1 minus 1 cos of theta, K1 member force AB, member force contribution here under the unit load effect, minus 1 cos of component will come, minus, since this component will move in a left hand side, that's why K1 comes to be 0.7071 kilonewton compressive nature. Summation of Fy equals to 0 result into a relation K2 minus 1 sine of theta equals to 0, resulting into K2 value as a 0.7071 kilonewton compression in nature. Now next joint, if I move to the joint A, we'll have three forces here, K1, K3, K5. Among this, K1 is known to us. If we write static equilibrium equation for this free body diagram, we get a relation summation of Fx equals to 0, K1 minus K3 cos of theta. If I take horizontal angle with horizontal component, then the K3 component will be here, cos component here, so it should be minus K1 plus K3 cos of theta equals to 0, so resulting into value as K3 equals to 1 kilonewton. If I write summation of forces in vertical direction, we get value here, relation here like K5 minus K3 sine of theta, K5 going upward minus K3 sine of theta component going downward, resulting into value of K5 as 0.7071 kilonewton in compressive nature. Next we'll go to the joint D, where we'll have three forces here, one unit load applied, K4 the horizontal force and K5 the member AD force here. So we know K5 force here, we know unit load here applied here, unknown force is the K4 only, that's why I will write equilibrium equation along the horizontal direction only, so resulting into a relation minus K4 plus 1 cos of theta equals to 0, that's why K4 value comes to 0.7071 kilonewton compressive in nature. Likewise, we have find out the contribution of this unit load among all the members here, which are compressive in nature along AB, BC, CD and DA, whereas it has a tensile nature along the member AC. Now after knowing this P and K forces, I will put this result to get the final value of redundant force, and for that we will have a tabular format to have easy in the calculation, representation of tabular format to have easy in the calculation. Members, first column will be members AB, BC, CD, DA, AC and BD. I will take care that flow of the member should be remain unaltered, like I have taken first periphery element, then I have taken inclined members, then I have put the respective P force carried by that member. In case of statically admissible part, AB was having 0 magnitude, BC W kilonewton compressive nature, CD W kilonewton compressive nature, DA 0 force, and AC minus 1.414 W because it was tensile in nature. Whereas if we see the BD member was removed, that's why I put here 0. Now if we go towards the K unit load contribution, K forces, the member AB was found to be 0.7071 compressive nature, that's a positive. Similarly, BC, CD and DA has the same magnitude compressive nature. AC was found tensile in nature -1, and at BD we applied tensile unit load, that's why -1 kilonewton here. Length of the members are given to us. For horizontal span we have 4 meter, and for vertical span we have 4 meter. That's why peripheral members will have 4 meter length, whereas the inclined member will have a length which comes from a geometric constants like 4 square plus 4 square. If we take root of that, resulting into a value of 5.65 meter. Now what I will do, I will take a product of PKL, uh, where the product will be, for the case of AB it will be 0 because P force is 0. In the case of BC it will be W multiplied by 7071 into 4, resulting into 2.82 W. Likewise I will do the calculation for other members, and finally what I will do, I will take a summation of all the values here uh, to have a cumulative effect of P and KL product. It comes to 13.64 W. The second column, it relates to the unit load effect, K square L. We will have a relation here, K square. I will do the squaring of this column number 3, 0.7071 square multiplied by the length 4, resulting into value of 2. Likewise, I will do the calculation for all the other members, and the summative value comes to be 19.30. We have proved from the Castigliano theorem that redundant force X is given by the relation minus summation of Pi Ki Li divided by summation of Ki square Li, where we have assumed here area and model of elasticity as a constant as it was given in the statement. So what I will do, I will put the summative values here like minus 13.64 divided by 13.30, 13.64 W divided by 19.30, resulting into a value of minus 0.707 W kilonewton, which was assumed initially tensile, means it should be compressive in nature. But what I will do, I will under the effect here while calculating the member force, I will continue with the negative terms here. So let us find out the final member force. For that, again I have prepared a tabular format which have following particulars. First the members here, second P force, next one is K force, and next the third column is about X force, where I have put the value what we have got. It is negative, I will substitute here negative itself. Then last column will be a combination of this, the product here, Fi is equals to final force in member is equals to Pi, the force in the determinate state, plus the contribution of redundant force X into Ki. Ki is the factor how this redundant force is being distributed. For the first case the P force is 0, and then if we take a product here X into Ki, so we get here 0.707 multiplied by minus 0.707, means the negative answer I will get, it is about minus 0.5 W, means it is a tensile in nature. Whereas if you go towards the BC, it has a magnitude W, 0.707 plus 0.707 into minus 0.707, means it is a negative component. If you take a summation of this one, it resultant value will be 0.5 W, the positive value. That's why I put here compressive in the nature of the force here. Likewise I will do the calculation for all the members, and the final forces will be written like this. Okay, hope you understood the application of Castigliano theorem to find out the redundant force within the indeterminate structure given frame with the help of unit load application. So we'll meet with more numerical in next in upcoming lecture. So stay tuned and stay safe, be at home and stay safe, be healthy. Thank you.